Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. Our seminars are streamed live on the third Thursday of every month at 10 a.m. Central Time and available to watch anytime on our YouTube channel. If you missed any of our outstanding presentations so far, again, I encourage you to check them out on the YouTube channel. Also, please stay tuned and join us for our upcoming seminar speakers, a few of whom are shown here. Before we get started, a great big thanks to Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and two CMCC students without whom the seminar would not happen, Quintarius Moore and Noah Sheehan. Also, thank you so much ahead of time for joining us. Please subscribe to our YouTube channel to watch all of the seminars and follow us also on Twitter. Quick guidelines, the seminar is being recorded. If you have questions, please email them to us at cmccdiscussions@gmail.com, or you may post them directly in the YouTube channel. They'll be propagated to the speaker to be answered at the end of the seminar. Finally, I'm very pleased to introduce today's speaker, Dr. Timothy Hanusa. Tim Hanusa received his bachelor's degree in chemistry from Cornell College in Mount Vernon, Iowa. He received his PhD in 1983 from Indiana University Bloomington, working with polyhedron heteroborons under the direction of Lee J. Todd. After postdoctoral research on organolanthanides and organolanthanide catalysis with William J. Evans at the University of California, Irvine, he joined the chemistry faculty at Vanderbilt University in Nashville, where he is now a professor of chemistry. His research has focused on organometallic complexes and catalysis with the main group elements. More recently, he is investigating mechanochemical approaches to organometallic synthesis with metals from across the periodic table. We're looking forward to having Dr. Tim Hanusa as part of our seminar series.
I'd like to thank you for that introduction. It's a privilege to sort of join these mechanochemical discussions. What I'd like to do today is tell you a little bit about my own personal journey into mechanochemistry, coming from someone who had been involved in solution-based organometallic chemistry for a long time, and how mechanochemistry has really changed my viewpoint on how to approach reactions and the potentials for new types of chemistry. I think it's been mentioned by others about the deep roots that what we would now call mechanochemistry has, going all the way back to the ancient world. Even this Latin phrase about bodies do not react unless they are dissolved, which may be a mistranslation of Aristotle, but I think it reflects sort of the unease that many chemists, even today, have about the idea of running reactions without a solvent. And that's it's something that is really a fairly recent origin that we would sort of recognize mechanochemistry as it is. There's a textbook found even from the late 19th century that sort of categorically states one cannot assume that chemical changes come about through mechanical action itself. The idea that you can do reactions without a solvent just seems unnatural to a lot of synthetic chemists, and it's been something that's been, I think, a slowly permeating through the community, but it's sort of, there's a lot of pushback against the idea. And it wasn't really, actually a few years after that textbook was written, that people like M. Carey Lee, sometimes called the father of mechanochemistry, although other people have had that title as well, but first sort of distinguished it clearly from thermochemistry. And only a bit over 100 years ago do you have someone like Wilhelm Ostwald, who actually introduces the term mechanochemistry. So it's not of as long a standing origin as we might sometimes think. Of course, the International Union of Pure and Applied Chemistry now has this definition of a chemical reaction that's induced by direct absorption of mechanical energy, sort of a fairly broadly encompassing statement, because mechanical energy can take many different types of forms. There's surface friction, there's sound, there are shock waves, there are bond stretching, and the trituration, the grinding and milling, which is going to be the emphasis of ours today. But actually, mechanochemistry encompasses a wide variety of different types of activation forces, and encompasses really all of chemistry in different ways. And I think as synthetic chemists, this is a question, and other people have pointed this out as well, the sort of paradigm shift that one has to sort of undergo when you think about mechanochemistry, because the classic question in solvent-based chemistry, what's the best solvent for this reaction? And I encourage you, if you want sort of an amusing video of the discussion of the best solvent for reaction, to check out this one that's on the slide. But in contrast, you really have to think about a new question. What happens if there is no solvent? You know, do I really need a solvent at all for this type of chemistry? And this is something that's takes a shift in sort of our perception of just how we even approach a reaction at all. I titled this thing about chemistry, or this talk about chemistry with a hammer. And it turns out that actually that phrase has been used before, and not in the context of actually mechanochemistry. There's a paper from 1987 that talked about the desorption of methane from nickel surfaces by bombardment with argon. And they actually called it chemistry with a hammer. But if you want to talk about a literal hammer, you can sometimes reference the festival of exploding hammers that takes place in Mexico, where explosives are strapped to sledgehammers and blasted on the ground, which sounds like a lot of fun. And a few years ago, Professor Ito showed us how you could use an actual literal hammer to borylate aerodioxines with piezoelectric materials by literal hammering. And when I first got started with mechanochemistry, one of my students was sort of a fan of Marvel Comics, and we used to use sort of the hammer of Thor, Mjolnir, over an arrow to represent mechanical activation. Later on, we switched to using 3 circles as a more universal symbol, and that's what I'll be using today to represent grinding and milling going on. And if you're not involved with mechanochemistry now, I really encourage synthetic chemists to give it a shot, because it can be done with any large range of different resources. And you can start with the mortar and pestle, which many people have. It's virtually every lab has it, and it's cheap, and you'd be surprised with the amount of chemistry you can do with it. There are obviously some limitations. It's how reproducible it is. It's pretty tedious to grind for 20 or 30 minutes for a reaction, but it can get you started. If you've got a vortex mixer in a lab, which many of them do, just vibrating a top, you can add some stainless steel balls to a vial and watch a reaction occur, get more energy that way. If you want to bump up the game a little bit, you can buy so-called tube drives, which have a propeller to give you more energy. We did a lot of our early chemistry with a device like this. And of course, if you really want to get invested, there are things, mixer mills, which will cost in the order of several thousand dollars. These have vibrating jars, and they've been illustrated in other videos in this series. And of course, going up even farther, there are planetary mills, which will set you back sometimes tens of thousands of dollars, depending on how fancy you want to go. They have larger capacity, somewhat different energy applications. But the point is that mechanochemistry can be done over an enormous scale of different types of resources, and its equipment shouldn't really be anything to hold people back from getting involved with it. You know, there are pitfalls in synthetic chemistry that I sometimes think aren't given enough care about, because it's people have recognized it, but I think sometimes it goes under the radar. One of the cases where it was definitely pointed out was an early reaction where sodium ACAC was reacted with chromium trichloride, and it was ground together, and a pink powder resulted, and then it was heated up, and out from the reactions was a sublimate of the tris ACAC chromium. That sounds like a pretty good mechanochemical reaction, except the people who did this also looked at this pink powder and found that there was no chromium acac at all. All the pink powder represented was a very finely ground mixture of the starting materials, and it was the heat itself which is what drove the reaction and produced the mechanochemical output. It's even more subtle when, let's say you have a white powder and you grind it with another white powder and you get a white powder. And how do you know that anything has happened? And this occurred to us a few years ago when we were looking at the reactions of different types of bulky amides. And you take calcium iodide and grind it with this particular potassium amide, this hexamethyl disilazide, and you get a white powder out. In this case, we could actually look at the ground powder before any other thing touched it, and we could see that it, by powder XRD, X-ray diffraction, there were the lines characteristic of potassium iodide. Presumably, the calcium amide was amorphous and didn't show up, but the fact that the potassium iodide was there showed that the reaction had occurred. But often, because workups in organometallic systems, we can't sublime products out, and often organic solvents are used to extract the product. One has to be very careful that the reaction has really occurred on grinding and it not after the addition of the solvent for workup. As a little sort of background to the mechanochemical reactions, I wanted to tell you just briefly about the synthetic chemistry that brought us to the mechanochemical counterpart. This is something that started about 20 years ago when we were looking for new types of catalysts for polymerization, and we're investigating allyl compounds of different transition metals. And I looked at some of the literature properties described for some of these homoleptic compounds, the ones that have just only allyls or sometimes a phosphine on it. It's kind of discouraging. They had a lot of thermal instability problems, decomposing or exploding at low temperatures. And that's because the allyl is a very small anion and it can easily undergo oxidation to a radical, and the radicals can couple, and then the whole reaction falls apart. It turns out that you can block, or at least strongly inhibit, that reaction by substituting on the allyl. And so this is a space-filling drawing of the allyl anion, the parent anion, and you can put on a group like trimethylsilo or tert-butyl, and it bulks up quite a bit. And you can put on 2 and you can put on 3. And if you look at the volume of these molecules, they're anywhere from about 2.5 to 5 times larger, but they're still allyl, electronically allyl. It's just that you've really bulked them up sterically. So this slide I could have shown you a dozen years ago, where we would make the alkali metal salts of these different substituted allyls and mix it with a metal halide, in this case, like a dihalide in some sort of ether solvent. We'd precipitate out the potassium halide byproduct, and we get out our, in this case, a diallyl species. And pretty good yields, and usually there's no thermal instability problems. So this is the background that I wanted to let you make sure that you're familiar with before we went into the sort of mechanochemical analogs. So when I think about the differences between mechanochemical and solution-based reactions, I sort of divide them into 3 different types. There are the ones where the solid state and solution syntheses can give very similar or related products, even though there are differences. And I invite you to look at this review article that discusses some of those. There are cases where solvent is still needed. And I don't think of mechanochemistry as a panacea for all synthetic difficulties, because solvents do a lot more than just disperse reagents. They also disperse heat. And so if you have a very exothermic reaction and you're grinding things together, you can sort of cook your product if there's no solvent around there to sort of soak up the heat. But of course, the fun stuff is when the solid state gives you an unexpected or new product that you can't get in solution. And that's when it really gets exciting and sort of expands your vision of what synthetic chemistry can bring you. But in the nature of type 1, the ones that I sort of called solvent optional reactions, there's really a wide range of organometallic species that you can see, everything from the venerable ferrocene up at the top, different allyl compounds that we've made, carboranes, cyclopentadienyl species, even this mixed metal complex. And in all these cases, you can just grind the reagents together or conduct the reaction in a solvent. And sometimes the yields will be somewhat different, but basically you get the same things out. It would be nice if we had greater predictive power for this to say confidently, yeah, it's safe to take the reaction out of this reaction and it will go without any problem. We're not quite there yet to be able to say, yeah, that solvent plays no critical role in there, but that would be ideal. And I also don't want to suggest that it's only single products that are solvent optional. There are whole reactions that people have investigated with this. This is olefin metathesis that can be done, of course, in solution, but also in the solid state. James Mack has shown us that you can use metal foils or grinding jars, in this case, to do like cyclopropionation reactions. It also happens in solution with silver salts, but you can do it in the solid state. Professor Ito has shown us about Suzuki couplings that can be done in the solid state, also can be done in solution, not as great a yield, but I think of these as sort of the solvent optional reactions, the ones where solvent plays a role, but you can usually dismiss it if you want to as well. There are times, though, where there are some interesting and some subtle differences that can be exploited. This is a case of a reaction that looks very straightforward on paper, and in fact, that's how it was originally described, of taking bis-cyclopentadienyl dichloride and treating it with potassium terpbutoxide and just substituting off the chloride. Turns out it's not really quite as simple as that. When you actually run this reaction, there are 4 different products that you get out of this, not just the simple dichloride, but also reactions that involve loss of cyclopentadiene and actually a gain of 1. And if you do it in THF, it's true that the major product is actually the one that you sort of naively expect, about 70%. But that shifts if you run the reaction in hexane, and in fact, you get more loss of the cyclopentadiene. And curiously enough, if you do this just by grinding the reagents together, it's not so different, at least in the 2 major products from that you get in hexane. And it suggests a different type of environment, that perhaps the mechanochemical environment is a more nonpolar environment than that provided by ethers. So it's a shift. The reaction, you still get the same products, but not in the same distribution. We saw this also several years ago when we were looking at the group 15 allyls, and these are compounds of arsenic, antimony, and bismuth. You can make all of them in solution or mechanochemistry. Sometimes you have to make some adjustments in solution, but all of them are accessible either way. What was interesting, though, is that you didn't always get the exact same composition of products. In the arsenic case, for example, it turns out there are 2 distinct species. There's a completely asymmetric one shown on the left, and one that has 3-fold symmetry, C3, that's on the right. And if you look at the NMR of these, you see both these products in solution, and this is just one portion of the NMR of the quote asymmetric one, that there's 3 peaks that are associated to the C1, the asymmetric isomer, and a much smaller peak that's representative of the trifold, the higher symmetry diastereomer. If you do this reaction in solution, you see a lot more of the C3, although all 4 peaks are there. And so basically what's happening is that by doing this in the solid state, you're tipping the balance towards the asymmetric form. And the question comes up, why is this? And this is a case where it seems as if the actual structure of the solid plays a role in shifting the balance of diastereomers. Arsenic triiodide, for example, has this layered structure as shown in A. And it turns out you can do some molecular modeling to show that if you have these really bulky allyls, such as the ones we're using, they have to come in parallel to the plane of the ions so that they can actually get close enough to bond. And that starts to set the stereochemistry around the center, and you end up with a preponderance of the asymmetric form. In solution, of course, you've got a much more sort of spherical environment, and so you don't have this preferential directing force that you get with the lattice. Again, you get both forms, but there is a shift towards a a preferred form, the asymmetric form in the solid state. And I think this general property about the importance of the solid state structure needs to be given a lot more attention in organometallic synthesis, because I think there's a lot of potential for tuning the outcome of reactions based on the structure of the crystalline structures of the reagents. There are cases when, what I like to call type 2, where the solution synthesis gives the product we want, and the solid state doesn't, although that's a place where we're trying to push back as much as we can. But where we first encountered this was back in the old days when we were doing everything in solution, and we had made a variety of first row bisallyl compounds of chromium and iron and cobalt, and nickel was always the one that we couldn't figure out what was going on. We tried different halides, and things that we always got were just the allyls that had coupled together. This is a product of radical coupling, and it's a nice compound. I mean, these two allyls get together and couple. But it was like, what was the problem with nickel? And it finally occurred to us, maybe we should have thought about this sooner, but in fact, the anhydrous nickel halides are really not soluble in THF. And so you can put them in a solvent, but they're really not dissolved. What you have is a slurry, and these solid undissolved nickel halides actually serve as a point of coupling for these reagents, and I think that's what contributes to the outcome that we see, that the allyls would rather couple than bind to the nickel. So the solution to this problem was to just use a more soluble reagent. So this is the dimethoxyethane adduct, although there are other ones you can use. And whammo, we got our product, our allyl. It's a really bulky allyl, as you might expect. And so you might think, well, game over. We solved our problem. But we have more recently gone back and looked at this reaction just to make sure that we weren't sort of fooling ourselves. And sure enough, if you use the nickel bromide DME with the potassium allyl and just grind them together without solvent, you just get the coupled allyl. And so it seems like solvent really is necessary to make this work. Well, to sort of check this out a little more thoroughly, we went back and looked at all the different reactions of chromium and cobalt and iron without solvent, and it turns out that almost all the time you get the majority of the product is this coupled allyl. Chromium gives you a little bit more, but of the product, but in that case, the yields of everything are really dismal. So it really seems that you take out the solvent, and these reactions do not give you what you want. So a standard approach to try to addressing this issue is to look at the idea of liquid assistant grinding. This is a concept that's been around for a while, sort of beautifully demonstrated in this paper by Tomislav Frišić and others when they were looking at the formation of co-crystals. In this paper, the idea of looking at caffeine and grinding it with citric acid or citric acid hydrate did not result in any product. But if you just added a small amount of water to it, or if you made a caffeine hydrate and then ground it with citric acid, you could get this co-crystal. And sort of emphasizing the point that hydrates could serve as a sort of a surrogate source of solvent in reactions under certain cases. So the whole lag system has been quantified in the sort of eta scale. And in case you're not familiar with it, it's defined as the microliters of solvent added per milligrams of total reagents, or milliliters per gram. It's conventionally sort of expressed in a scale like this, that the lag region sort of lies somewhere between 0 and 1. And as you add more and more solvent, you get visible pastes and slurries and eventually get to solution. The idea, though, is that the lag is sort of serving it as a lubricant, or modifying the surface properties of particles, that the solubility should not really play a role in that it's actually been described as a catalyst. In organometallic chemistry, it's a little unsettling, because the eta scale is just a volume per mass measurement. So the identity of the solvent, how polar or how basic, how hydrogen bonding is not really considered, and especially the relative molar masses of the solvent and reagents aren't taken into account. And this is to show you how that can lead to some issues. Here's are the reagents that one would mix together to make the well-known compound ferrocene. And this is the iron chloride and sodium cyclopentadienide. And if you add just enough THF to put you at the eta value of 1, which is sort of formally in the lag region, it's clear that a reaction has occurred without any grinding at all, reduction in volume. And when you do a little bit of math and look at how much THS have you really added, it turns out there are almost 3.7, almost 4 molecules of THF for every single iron center in the mixture. It's not just a trivial amount. You'd have to go way below a value of 1 to have just a sort of a trace amount of solvent. And so this scale has to be taken with sort of large grains of salt, and especially when it comes to mechanochemical properties. And so we went back and looked at our reactions of our diallyl first row metals with both 5 equivalents and 10 equivalents of THF. Turns out that in every case, solution, although that helped, solution was still usually better than these amounts, even though we are pretty much in the lag region or just slightly above it. Nickel, of course, was sort of the hopeless case. It never really seemed to help at all. But these seem to reinforce the fact that you can't really dismiss solution in all the time. So with nickel, we thought, well, maybe we're too much in a rut with THF and start to explore other types of solvents. And one of our first sort of breakthroughs happened when we tried pyridine, which is not as often used in organometallic synthesis, but it turned out that we could use lag with pyridine, and this is an eta value of 0.7, although it's actually 5 equivalents per nickel. We're actually getting almost 30% of our nickel species. And so that started thinking, okay, we need to sort of think outside the box a little bit. And then finally, and I have to give credit to one of my students, Henry DeGroot, who wanted to look at how solvates would play a role in this. And so what he did was take the tetrapyridyl solvate of nickel dichloride. It's a well-known discrete compound. It's a solid, and obviously has 4 pyridines per nickel center, although on the eta scale, it'd be about 0.55, and very cleanly gave you almost 70% yield of the diallyl nickel, with no evidence at all of the coupled product. So this has really started to change our thinking about lag and the importance of using solvated reagents in our sort of chemistry. It's an area that I don't think that a lot of organometallic chemists usually think about, because it sort of combines an overlap of coordination chemistry and organometallic synthesis. And it's something that we're very much interested in pursuing, because I think there's a lot of potential in this sort of stealth introduction of solvent in a solid form into mechanochemical reactions. Finally, I want to talk just briefly about some of the cases where the solid state synthesis gives you unexpected new products, and you can't really get them by solution. Sometimes it's a fairly straightforward case. This is an example where we were trying to look at some beryllium chemistry and particularly indeno beryllium compounds, which had never been reported in the literature. That's kind of funny, because cyclopentadienyl compounds have been known for beryllium have been known for over 60 years. And indeno's usually sort of considered, first cousin to cyclopentadiene. It's a benzo CP. And whether people had tried and just never reported it, but in any case, when we tried it with different solvents in different cases, we couldn't get anything out other than just maybe starting materials or just decomposition species. Turns out, take out the solvent and grind it, and you very rapidly form the diindenyl beryllium that has a very similar structure to beryllicene, but it's just a case where solvents just interfered with the coming together of the rings on beryllium. So this is a very simple case where solvent just is not your friend. And after we had made this, you could take the compound into to benzene or any sorts of hydrocarbon solvents, and it's perfectly fine. It's just that initial synthesis step that ethers really interfered with things. There's another case that actually started in our sort of solvent era when we were looking at or looking for new types of initiators for different types of polymerization. We had made this magnesium compound that had 2 THFs on it, and turned out that it was sort of dead. We were looking for something that would polymerize methyl methacrylate, MMA, that makes plexiglass or lucite. Turns out it was completely dead. With a little modification, we could still do some synthesis chemistry. You could make a diethyl ether complex by the same sort of halide exchange, and then rather tediously put it under vacuum for a week, and you could make an unsolvated species that dimerized. And it turned out it was active in methyl methacrylate polymerization. So this gave us some hope that, okay, maybe THF was blocking your activity, and this seemed like an ideal sort of case to use mechanochemistry at, because we could save this week-long desolvation process and get to this compound directly. So when we tried that, didn't quite work. At least didn't give us the product that we expected. We ended up with this polymeric species, which is just a fragment of which is shown here, that has both potassium and magnesium in it, magnesium in an unusual bonding mode, but this is actually a coordination polymer. And not only that, the ratio of the parts of the compound don't really follow those that we used to make it. In fact, the reaction makes sense if it was a 4-to-1 reaction of the allyl anion to magnesium bromide, even though we only use 2-to-1. Obviously, your yield is going to take a hit because of that. But this is actually something that we have seen in a number of different cases where the stoichiometry of the product does not match that of the starting materials. And I think that's partly a consequence of the mechanochemical environment, that you have a high concentration of reagents. We're seeing kinetic products rather than maybe the thermodynamically favored products. The fortunate part here is that we do have the particular material was actually more active than the magnesium dimer that in methacrylate polymerization, and so it was sort of a bonus. But I think the fact that we are incorporating potassium is sort of indicative of the fact that things are in a single phase. This is a one-phase system, and you don't have the effective solvents that can precipitate out a reagent and sort of clean up a reaction. Everything's together, and if your byproduct is around, it can react with whatever's there in solution. And of course, the case of triallyl aluminum is an interesting one, because it's one of the first things that we did when we were getting involved in mechanochemistry. And it came about because of sort of curious fact that just the simple unsolvated parent triallyl aluminum is, to my knowledge, still unknown. And this goes back to work of Grignard himself in the 1920s. And you think, what's the problem? I mean, there are virtually all the other sort of simple trialkyl aluminums are known. What's the problem with triallyl aluminum? Well, it just seems that whenever you try to make it by different routes, you always end up with mixed species that have allyl halo components in it, and it's not a clean reaction. You can make solvated versions, and so I specifically want to say that it's the unsolvated version that's not known. Solvated versions, it's not a problem. A dozen years ago, Juno Kuda showed that you could do a simple halide exchange and make this THF solvated complex. You could substitute off the THF with different bases, such as pyridine or triphenylphosphine oxide, but you couldn't make the unsolvated version. We thought initially, and that, oh, well, what our bulky allyls, that will sort of come to the rescue and we'll be able to make these sorts of compounds. Turns out, no. We tried different ethers, different halides, different temperatures. All we got out were oily goos from this. We tried hexanes. You saw no reaction. We tried deprotonating the propene, which is the precursor to our allyls, and that didn't work at all. What did work was, of course, taking out the solvent, and you grind for 5 minutes, and wham, you get your triallyl aluminum. And it turns out that it actually reacts with THF, decomposes, which is why we could never make it in THF. And it didn't really occur to us that it would be so highly reactive, and you can scale it up. And although trial 3-quart aluminum is not unprecedented, it's reasonably rare. It's not commonly encountered. So we were interested in looking at some of the reactivity of these species. And one of the first things we did was to treat it with benzophenone, and it underwent an insertion reaction. And that wasn't unexpected. That's sort of what you would anticipate with something like this. What was surprising is that it did it immediately. I mean, as soon as you injected a solution of benzophenone in this, you got an immediate color change and the production of this product. And Juno Kuda had actually reported a similar reaction with his solvated parent compound, and he said it took 10 minutes at room temperature to do it. And so the question was, why is ours so fast, given the fact that we've got all this bulky allyl that might interfere with things? So we did a little bit of sort of simple modeling of this to sort of see if we could understand some of the energetics of what's going on. And of course, triallyl aluminum parent compound doesn't exist, but the computer doesn't know that. And so you can model it. And the first step in this reaction is attachment of the benzophenone to the triallyl aluminum. And if you start out with just the unsolvated version, there's actually a reasonable driving force, about 10 kcals per mole. But if there is actually THF on the molecule to start with, as in the bottom picture, and then you try to bring in a benzophenone to it, it's actually not spontaneous. And this is not a perfect model because the reaction does eventually go. But the point is that I think the difference is that you're going from a 3-quart aluminum to 4 in the top reaction, which is a favorable reaction, whereas in the bottom you're going from a 4 to 5, and it's just not as favorable. And so that really got us interested in the possibilities of generating low coordinate metal complexes that could display higher reactivity than normal. And we've been investigating that in the case of some different types of polymerization reactions in conjunction with the group of Brian Long at University of Tennessee at Knoxville. And it turns out that the triallyl aluminum will ring open lactide to form polylactide, which is a biodegradable polymer. It's not the world's speed champion, as shown in the blue line below. We eventually get to about 80% conversion after 5 days or so. And compared to an aluminum alkoxide, which is sort of a standard aluminum reagent, it's much, much slower. On the other hand, under these conditions, we do get a little bit better control of polymer dispersion of the different, the dispersity index is a little bit smaller. And there's a lot of room for tuning and tweaking things here. So the fact that we do get this reactivity is an encouraging, I think, sign for what the possibilities are going forward. And the last thing I wanted to tell you about is cases where mechanochemistry has given us some really interesting chemistry of probably absolutely zero use because the compounds are just too strange and too difficult to handle. But the chemistry is still fascinating in any case. This started out, again, in our sort of solution days from a paper from a different group, the Layfield group, who described the formation of this tin stannate. So it's a tin 2 compound, has 3 alleles, the same alleles that we've been using with the trimethylsilos on the 1 and 3 positions. And in solution, they got this stannate that is an anion, and that the counter ion was potassium with the THF on it. And we looked at that compound. We thought, this would be an interesting compound for making other types of mixed metal heterometallic species, because we could knock off the potassium and then use it to make new types of compounds. Or maybe we could even adjust the stoichiometry and make a diallyl tin complex, which no one had ever seen before. So we thought mechanochemistry might be an easy way of doing this. We avoid the complications of THF and see where it takes us. Well, you grind that, and in fact, what you get out are the stannates again. This 3-to-1 reaction, there's no THF, obviously, and because there's no THF, this actually links together and you get a coordination polymer in the solid state. A thing I want to point out is, once again, the stoichiometry of the product does not correspond to the stoichiometry of the reagents. We've got a 3-to-1 ratio of allyls to tin. We started out with a 2-to-1. And also, once again, here's our friend potassium showing up in the product. Did not precipitate out, obviously, because there's no solvent, but it gets incorporated into the product as well. And so we thought, well, if tin really wants to have 3 allyls around it, we're not going to get a very good yield with the 2-to-1 ratio of this. Let's bump up the ratio to 3-to-1, because that seems to be what it wants to do. So we did that, and instead we got a totally different product when we ground it. Now, actually, we initiated a redox reaction so that the tin-2 in the SnCl2 now got oxidized to tin-4, and we also had production of tin metal, tin-0. This was, and it turns out it's a bonus, it's also chiral. This had never been crystallography characterized before, a tetraallyl of tin. And then it gets even stranger. If you grind this for a longer period of time, say 15 minutes, you now get out, again, a redox process, but you get out a mesoform of this compound. And these are discrete species. We have crystal structures of both. They have different chemical shifts in the tin NMR. And it's really quite remarkable reaction that's never been observed in solution before. And I should say, oxidation has been observed in other sorts of mechanochemical reactions, usually when there's an explicit oxidant that's been added, but this is an internal disproportionation reaction that's being observed here. One of the things that made this chemistry so difficult was how unstable the tetraallyl tin was. Basically, we had an hour of working time, which is in hexane. You could try to grow crystals and get your compound out of solution. If you wanted to take an NMR in benzene, it's kind of good luck. I mean, you could put it in there and 10 minutes, within 10 minutes, you have solids falling out of that. And the question is, why is this so unstable? We thought maybe it was a steric problem, because tetraallyl tin, the parent compound, is known. It's air and water stable. And if you calculate the percentage of the coordination sphere with this program called Solid G, and it gives you this so-called G complex value, which is the percentage, the fraction of the coordination sphere that's sort of occupied by the ligands, it's about 70% with tetraallyl tin. In our cases, if you do the same calculation, we're pushing over 95%. And so, although there's not a sharp cutoff about when a compound becomes unstable, these are really, really crowded molecules. And so it kind of makes sense that maybe they would like to relieve such pressure. But then why are they so stable in the solid state? I mean, they fall apart in solution, but why in the solid state? And I think this is a case of that these represent dispersion stabilized compounds. These are a group of molecules that have received a growing interest in recent years, where there are a lot of very close interligand contacts, hydrogen-hydrogen contacts, shorter than the sum of van der Waals radii. And these dispersion interactions actually hold the molecule together in a sense, in the solid state. What's critical is that if you put these into solution, the solvents can disrupt these reactions, and then the molecule falls apart. And we were actually able to model this computationally and showed that if you turn off dispersion interactions, the bond strength drops by about 40% in these cases. So these are really overcrowded molecules available only by mechanochemistry, because you'd never make them in solution. They would fall apart before you could ever put them together. So to sort of sum up, I think this little brief story of where we've been, I'd like to stress that I think mechanochemical synthesis is a complement to solution-based organometallic synthesis. I don't think, at least right now, that it's going to displace solvent as all, but I think it's another tool that should be in the sort of the repertoire of synthetic chemists. It has advantages and provides certain routes to compounds that just often aren't available in ordinary solution-based synthesis. I think the issue of solvates needs a lot more attention, and something we're looking into as well. But the idea of solvates as a sort of a subset of lag, but sort of solvate assistant grinding that can bring in solvents in sort of a stealth manner into reactions and can provide a lot of the benefits of lag, but in a completely sort of controlled environment, especially the number of molecules of solvent per reactive metal center has a lot of potential there. And then, of course, and as other people have mentioned, you really have to rethink what I like to call the parameter space of reactions. You know, what are suitable reagents? I mean, the issues of solubility don't play the same role as they do otherwise. And the types of products that you can get out can differ a lot between solid state and solution. So it's a type of chemistry that has enormous potential, and I think really needs to be brought into sort of the mainstream of synthetic thinking in organometallic chemistry and actually in all branches of chemistry. Of course, I didn't do all this work, and I have to acknowledge many talented graduate students who've been involved in this work, both graduate students and I should say undergraduates as well over the years. I have to thank the people who've been involved in the crystallography of this, without whom many of our compounds we wouldn't be able to characterize completely. I have to thank the group of Brian Long and his students at UT Knoxville, who've been doing some of the detailed catalysis studies for us. These people for support. And again, thanks for the invitation to come and speak with you today and share some of the work that we've been doing. It's been a pleasure. And I'm happy to take questions that people might have.
Great, thank you, Tim. We have a few questions from the audience. Let's start here. The solid state reaction of arsenic iodide, for that case, since the allele has to come in a particular orientation, does the direction of force matter? For example, might shear matter more than compression?
Yeah, that's an interesting question. You know, we were just modeling this with sort of a small fragment of the lattice, and you know, that's actually something that we haven't looked at yet. You know, looking at different types of mechanical, because you can look at, you know, the difference between mixer milling and planetary milling, and you know, you get different types. Planetary is more of a shearing force than that of mixing. That particular reaction was actually done in a planetary mill. So that's a possibility. We've got a lot of things that we have on the sort of the shelf when to look at the differences of you know, the structure of the solids is making it a difference. But it does seem that it does play. And in fact, as you go down from arsenic to antimony to bismuth actually showed that the preference really wasn't there because it doesn't have the sort of layered structure. And even the structure of antimony is kind of a zigzag one. So the most pronounced difference is with this very laminar type of structure, and a shear force might be critical to making it work. It's something that we have to look at.
Thank you. Here's a related question, I believe, but something aimed at an earlier part of your talk. This is about the shift towards asymmetric,
right?
Towards the asymmetric form of the solid state. And they were wondering if the different types of instruments that you showed early on in your talk could affect the ratio or the amount of asymmetric form products.
Well, yeah, I think that is sort of related, you know, because different types of I mean, we started out with very simple things. In fact, I didn't mention this, but some of our first reactions were done with putting stainless steel balls in a glass flask on a rotary evaporator and just allowing it to turn slowly, and that works. I mean, it's surprisingly how simple you can get things to work. But I mean, really, it's an area we haven't investigated a lot about. We generally tend to use one instrument like mixer mill versus a planetary mill, depending on like the size of the reaction, because the planetary can just hold a lot more. So if you're interested in scaling things up, but they do provide different types of energy, and that's certainly an area that's got to be looked at more, whether different types of milling and different perhaps, you know, the density of different types of balls, whether you use, you know, stainless steel or zirconia or something like that, could affect the outcome. Yeah.
Thank you. We'll change gears a little bit. Could you please explain the coordination sphere and tell us explain what it tells us about stability?
Yeah. So in the case of the tin, it's just the idea of how much, if you have a lot of ligands, very bulky ligands, these will occupy a large quantity of the sphere. And if they are too bulky, basically they'll start to sort of collide with each other. And so that's what happens actually in the case of the tin species. It may have not been so obvious in those pictures, but there's actually sort of overlap in what you're seeing there is sort of projection from what each sphere has, starting from a point at the center of the molecule out, and the coverage of the ligands would actually interfere with each other. And so you have sort of an internal collision, if you will. And so sometimes the molecules will respond by backing off the ligands. They can't get quite as close as they would. And of course, if you're going to do that, you're going to have longer bonds, metal ligand bonds, which will be weaker, and that can then cause the molecules to be less stable. So this very tight packing of ligands around it sort of destabilizes the compound, because there's ligand interactions, and that can also affect indirectly then ligand metal bond lengths, which then affects the metal ligand bond strengths, and so the molecules become less stable.
Well, thank you. Let's do just one more here. So the effect of the solvent is quite complex and quite interesting. You mentioned that the solvent can interfere with the reaction directly, as well as carrying heat away, which could also interfere with the reaction. Might the solvent also facilitate the reaction by moving the reactants around?
Well, sure. I mean, that's what actually most people think about, the solvents, that they help in mixing. And I think in traditional sort of views of LAG, liquid assistant grinding, it's the idea that solvents on the surfaces of particles, say a monolayer of solvent, will help transport materials to and from the surface. I think what's interesting in our studies with the solvate assistant is that we have the molecules that are directly bonded. They're not just on the sort of the surface of a particle, but they're actually directly bonded to the metal centers, and that the reactivity is different from what we get with a lag type approach, where you actually add separate liquid solvent as distinct from having the solvent bound to the metal to start with. So yeah, I mean, solvents affect transport. They have an amazingly complex interaction with. So just to take out the solvent out of a reaction, a lot of things can happen. It's not simple, and the fact that so many reactions actually work as well as they do without solvent is sort of kind of amazing. That the solvent is there, but the reactions sort of do what they want to do and don't pay any attention to the solvent. But yeah, solvent's obviously important in dispersing and transporting reagents.
Definitely interesting and complicated. All right. Well, thank you so much, Tim. Really appreciate that.
Thanks. Yeah. Thanks for the invitation. Enjoyed it.
Thank you. Thank you, Professor Hanusa, for that outstanding presentation. And thank you so much for joining us. Please do check out all of our former presentations as part of the seminar series. They're shown here. For those of you who have seen this presentation before, you know that I've gone from 2 rows to 3. So the number of presenters we've had as part of the seminar series is growing, and we hope that you will check them all out. Also, we have a few upcoming speakers that we think you'll be excited about. Please do join us. Thank you again for participating in the mechanochemistry discussions.